Mr. Richard is the best. Mr. Richard is the best. Mr. Richard teaches classes. Mr. Richard, he wears glasses. Mr. Richard likes you dub. Mr. Richard's not a chub.
Welcome to our lab on measuring distances remotely, okay, or indirectly, I guess I should say. Obviously, with astronomy, there's lots of things that you have to measure, and you can't actually go there. Like, we've never been to the sun, but we know about that it's 93 million miles away. And when I say something like that, you should automatically have this curiosity signal inside of you going, well, how do you know that? How do they figure out how far it is to the sun without us actually traveling there? So I'm hoping that this lab will give you a little bit of insight about that. It uses what's called parallax, okay? And parallax just means, like if I hold this pen up right in front of me, let me get it to the camera. So right now it's just, if I bend down a little bit, it's right on the tip of my nose, right? Geez, I can't do it. Okay, right there. Now if I stop, I hold the pen the same, and now I move my head, do you see that it is no longer lined up? That is what's called parallax. It's kind of the same thing like when you're traveling in the car with like your dad, and he's driving too fast, and you look over at, or maybe your mom's in the car. This is a better example. Your dad's driving and your mom's in the car in the seat, and she keeps looking over at the speedometer, and it looks like he's going like 1,000 miles an hour because she's looking at it from a different point of view. And she keeps saying, you're speeding, and he keeps saying no, and it's all because you're looking at the same thing from a different point of view. Okay, that's parallax. So what we're going to do is, in the back of the classroom, you can see that I have set up a baseline. It needs to be straight, and in this case, I made it 3 meters long just because that was a convenient length. And what we're going to focus on is something way up here in the front of the room. Can you see the Rubik's Cube? Okay, so I have the Rubik's Cube set up there, and way back there is the baseline. So we're going to see how to measure how far it is away to that without actually traveling there, okay? And there are basically like 2 steps involved. We're going to measure from each side of the baseline, and we're going to measure the angle to that Rubik's Cube. The first angle is going to be 90 degrees just because that's convenient. Also, like, those of you in higher math, you probably know about trigonometry. And trigonometry has to do with right triangles. And so it's a convenient measure when we're dealing with right triangles and measuring distances. But don't worry, those of you that think that math is like a curse word, it's very mysterious to you. We're not going to do a whole lot of math here, okay? We can do this kind of without math. So we're going to measure, first of all, we're going to sight down a 90-degree angle right to the Rubik's Cube. Okay, so here I am in the back of the room. I've got 3 meter sticks end to end in a straight line. That forms what's called a baseline. I've got a 90-degree angle on the end of that. And I've got my laser pointer just sitting down, and you can see that it is pointed right to the edge of the Rubik's Cube in the front of the room. Okay. Uh-oh, I'm upside down. Well, I'm hoping you can kind of figure this out. I'm kind of using the document camera, and we're back here along that baseline. And I'm going to put it right over, and I'm hoping that you can see that. I think you can. So let me turn on the laser pointer, and I'm going to put it as close to the vertex as I can get. And I'm going to aim it at the Rubik's Cube. Okay. Can you see that I'm hitting the Rubik's Cube? Whoops, right there. I'm on the Rubik's Cube. And as I come down here, Whoops, I got to get it right on the vertex though. Let me try this again. Okay, I'm on the Rubik's Cube. If I tilt it down, you'll be able to see kind of what angle we're coming at. It looks like we're coming about right through here somewhere. And so when I move that away, it looks like about 67. Okay. Okay, so now what we're going to do is we're going to do a little diagram of this situation. At the bottom of my page, I'm going to put a 10 centimeter line. I'm just choosing 10 because it's an easy number to work with. And that is going to represent the baseline. Okay, does that make sense? So this is in actuality 3 meters. And then, remember one side of my my baseline, I measured it at a 90-degree angle. So I'm going to measure it at a 90-degree angle and just carry that up. So right now we're modeling the baseline. One side was 3 meters, and one side was and one angle was 90 degrees. And so now we're going to go to the other side of the baseline, and we're going to make a 60. What was it? 62 degrees, or 67 degrees, I think it was. So I put this right at the vertex. I go up here. My angle's coming out this way, so it hits 0 here. So I count up. I get to 60, 67, and I'm going to put a little tick mark there. And then all I need to do is connect. Can you see that? Let me make sure. I'm just going to draw a line right through the vertex and that angle. And I'm going to draw it. Let me move back. I'm going to draw it all the way up till it touches our 90-degree line. All the way through there. Okay? So I've made one big triangle from the vertex all the way to where it touches. So, what does this point represent? Remember, I had the 90-degree line on the baseline, the 90-degree angle on the baseline goes straight to the Rubik's Cube. I also had the other angle go straight to the Rubik's Cube. So the point where they intersect, that's the Rubik's Cube. That's the edge that I was trying to look at and find out how far it was away. Now you can figure this out in 2 different ways. People that know trigonometry would know that if we're trying to figure out this side here, okay, here's the hypotenuse. And then here would be, it doesn't matter what side you call it, let's just say side. So from this angle, this is the, we could figure out this angle, and we know that the, let's see, it's going to be the sine of this angle is going to be the opposite over the hypotenuse. So the sine of 67 degrees equals the side we're looking for over the hypotenuse. Oh, actually, that's not the one I want, is it? My bad. The one that we know is this one. So we would want the tangent. We want the tangent of 67 degrees, and we're going to go to the opposite side, which is the one we're looking for, and it's over 3 meters, which is the opposite over adjacent. Okay, people that don't understand trigonometry, let's not worry about that. Let's just do a simple proportion. If we know that the baseline was 3 meters, but the line that I drew on this little table here, down here, was only 10 centimeters. So 10 centimeters is representing 3 meters. I am going to measure this distance in centimeters. Let me just do it right now in front of you. Let's see, can I zoom away? Because you can't really see that, can you? Well, you're just going to have to kind of trust me, I guess. I'm going to start up here. Let's see, maybe I should start at the vertex. So I'll start down here at 0. And you can see I go all the way up, and it looks like I'm crossing almost exactly at 24. Okay? Pretty close. So maybe with a little bit of rounding, I'll just say 24 because that's an easier number to deal with. 24 centimeters. And so what I want to know is how many meters does that represent? So if you do a little math, just cross multiply. You know the proportions, the cross multiplying sums are equal. So 3 times 24 is going to be 72. And then divide that by 10. That's going to equal 7.2. And my units are going to be meters. So what I have predicted based on my angle calculations is that this leg is going to be approximately 7.2 meters. So let's see how close we are, okay? I'm going to measure this with actual meter sticks and we'll see. So there were 6 meter sticks up to this point, and just about exactly 7 to the Rubik's Cube. Okay, so we predicted 7.2 meters, and the actual distance was 7 meters. That's pretty dang close in my book. All right, I hope this helped you figure out how we can measure things indirectly.